In this lecture, we're going to be talking about the modes of our system. And we're going to first start off by talking about what is a mode of a system, and then we'll talk about the modes that show up in our aircraft. And really briefly, the modes just help us explain how the system is going to behave. So let's go ahead and get started. So as we jump in, let's first ask ourselves a question of what is a modality of the system, or a system mode. So when we come in here, we're going to first consider just a single state autonomous system. So what I mean by that is we just have, let's grab our pen. We have x dot is equal to ax. And we're going to assume that a is just a scalar. So we just have a single dimension, and we'll assume that x is also just then a scalar. So if we do that, this is the simplest ordinary differential equation that we have. We can immediately write the solution over time is that x of t is going to be equal to e to the a t minus t naught all times x naught. So wherever we start, we're going to multiply it by the exponential. And now we can see that where this a pops up. So the a ends up helping us know exactly how our system's going to behave over time. Okay, so let's just graph this out. And we're going to assume that t naught is equal to 0. It's an LTI system, so it really doesn't matter where t naught is. And let's just assume that we have, this is x naught. So we start off here up at, looks like a value of 2. So what we want to do is just see what the system does depending on what a is. So now let's do the simplest version. If a is equal to 0, if I could draw a straight line, this would correspond to a equals 0. So again, if a is equal to 0, then e to the a is just going to be equal to 1. And so x of t is equal to x naught for all time. Okay, so now if we said that a is less than 0, what we're going to end up getting is we have this exponential decay. So over here, this is a is less than 0. And if we do a is greater than 0, we're going to get an exponential increase, right? This is a is greater than 0. So the cool thing about this is that if we know a, then we'll know what we're going to do over time. We know how x will behave over time. And even more specifically, we know if it's going to blow up, we know if it's going to converge down to 0 or do nothing. Okay, so we've defined that really well. So now if we do a multiple state system, and again, it's going to be autonomous, meaning we're going to have no control input. We can write down that x dot is equal to ax. And now A is an n by n matrix. So A is n by n. Well, that was an ugly R. It's an n by n matrix, and that means that x is also an n-dimensional vector. Okay, so there's something very similar to the scalar exponential that we can use. This is a little bit more complicated, but it looks almost the same. We have that x of t is going to be equal to e to the a t minus t naught times x naught. Now, at face value, these look very similar, right? But this is the matrix exponential. Exponential. And this is the scalar exponential. So, if you were in, for example, MATLAB, this is be exp, and this would be expm. So they are different. They're defined very similarly, but you got to be careful. Anyway, so regardless, we now, given A, we know how our system's going to behave. But now it's a little bit more complex because we have an n by n matrix, and we don't know exactly how the elements of that n by n matrix are going to affect the system over time. Okay, so let's gain just a little bit of intuition from a discrete system. Well, let me go back to blue. And we'll look at a discrete system. And again, we've shown in previous lectures how we approximate our continuous system with a discrete system anyway. So if we have really tiny small steps, this is a great approximation. What we're going to talk about actually holds even for the continuous system though. So we'll gain the intuition and then leave it up to you to take a linear multivariable control to have us show you that it actually does hold for continuous systems as well. So let's consider our x naught to be a special case. We'll say that it equals v, where we're going to say that v is an eigenvector with corresponding eigenvalue lambda. Okay, so if we, and I meant to write our discrete equation where we're going to say that x of k plus 1 is equal to a times x of k. So we'll take a look at this. So we have x naught is an eigenvector. Now, you may have forgotten a little bit of what an eigenvector is, but eigenvector just means that a times v is just going to be equal to lambda times v, which is pretty cool. So it's just going to be, the output is a scalar multiple of itself. Okay, so now let's start looking at that. We'll say that if we look at x1 is going to be equal to a times x naught, which is equal to a times v, which we said is equal to lambda times v. Good. Let's keep going. x2 is going to be a times x1, which equals, I'm going to put the lambda out front, oops, lambda times a times v, which is just equal to lambda squared times v. Okay, if we did it one more time, x3, let's zoom in here, is equal to a x2, which is equal to, I'm going to put the, again, since lambda is just a scalar, I'm going to pull it out front. We'll have lambda squared times a times v, which is equal to lambda cubed times v. So we could then say from this that our x of k plus 1 of, I'm just going to say x of k will then be equal to lambda to the k times v. Okay, so if we're going to converge, if we want x to go down to 0, then we can take a second and think about what should the conditions on lambda be? Well, if we want x to go down to 0, then we better take that the magnitude of lambda must be less than 1. Okay, and that'll help us go down to 0, because then as we increase k, lambda to the k is going to be a smaller and smaller number, and we'll be able to have x then converge I should have put x of k. So if we want x of k to start to converge to 0, if lambda, the magnitude of lambda is less than 1, then we can, then we're good to go. Okay, now, so that was if we started on an eigenvector. Now, if we say that A has unique eigenvectors, eigenvalues. So this is just one more condition to make things just a little bit easier. but we're getting more complex as we go along. That means that all of our VI, V1 up to Vn, so n again is the dimension of our state, these form a basis. Now, if we have repeated eigenvalues, for Rn, if we have repeated eigenvalues, that's not going to necessarily hold, right? And we can, what we'll do is we can augment our eigenvectors, and the argument we're about to make still holds fairly well with some small changes. But just to get some intuition, let's say that A has unique eigenvalues. If our eigenvalues form a basis set for all of Rn, that means any value in Rn can be expressed as a linear combination of V1 through Vn. So this implies that any value that is in Rn can be expressed as a linear combination of V1 up to Vn, i.e., our initial state, x naught, which is in Rn, there exists an A1 up to An that are all scalars, such that x naught is equal to A1 times V1 plus A2 times V2 plus all the way to An times Vn. So our x naught is just can be written as a linear combination of our eigenvectors, which is pretty cool. So now let's look over time. Again, we have x of k plus 1 is just equal to a times x of k. So we can come in here and start doing something very similar to what we were doing before, right? We'll say that x1 is equal to a x naught, which is equal to, we'll have a times, and we know that we have this expression. We have a linear combination, so we have a1 times v1 plus, and I'm just going to write the first and the last terms, an times vn. Okay, well, this is equal to a1 a times v1 plus dot 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 plus an, capital A matrix, times vn, which is just equal to, each one of these eigenvalues or eigenvectors is going to have a corresponding eigenvalue that we'll call lambda 1 up to lambda n. So that means, since they're eigenvectors, we'll say that this is going to be a1 times lambda 1 v1 plus dot 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 plus an lambda n vn. Okay, so it's starting to look similar to before, where before we had just lambda times v. Now we have a summation of them. Let's do another couple. Oops, let's go back to blue. So we have x2 then is equal to ax1, which we now know, what x1 is, right? Which is equal to, I'm going to pull all of the scalars out front. So we have a1 lambda 1 a times v1 plus an lambda n a times vn, which, if we use the fact that we have a times a eigenvector on both of these cases, we'll get a1 times lambda 1 squared times v1 plus a1 times lambda an lambda n squared times vn. Okay, if we keep going, we have x of k then is equal to ax of k minus 1, which is just going to be equal to a1 lambda 1 to the k v1 plus dot 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 an lambda n to the k times vn, which is really quite cool. So if we want our system to converge, so x of k to go to 0 as k goes to infinity. So if we want that to happen, then we better have that we better have that lambda for any x naught, I should say. We better have that lambda 1, the magnitude of lambda 1 is less than 0, all the way up to the magnitude of lambda n is less than 0. Right? So if all of these values are less than 0, then we're going to converge. But regardless of whether or not they are less than 0, we can see that our system evolves according to our eigenvectors and eigenvalues, right? Scalar multiples of them, right? So we have a1 up to an multiplied by it. But as our system evolves over time, it just evolves according to the scalar multiples of these eigenvectors, which is really cool. So we know that then these eigenvectors form the basis for how our system evolves over time. So that's why we call these are the modes. We call our eigenvectors and values the modes of our system. So we know that how our system is going to evolve over time because it's going to be a linear combination of these basic modalities, which is pretty cool. And that linear combination is given from our initial state. Now, just another quick aside, right? We've done this for discrete. Again, for discrete, if we look at our real and imaginary axis for all of our eigenvalues, we're saying that the lambda must be less than 1 for convergence. For continuous, if you remember your undergraduate controls class, the unit circle maps to the left half plane. So again, if our real and imaginary, we need the real part of our eigenvalue must be less than 0. But regardless, our modalities end up staying the same. So our system evolution is still just a linear combination of how our original eigenvectors. Okay, so that's what it means to be a mode of our system. So we have these eigenvalues and eigenvectors that define the modality, define how our system's going to evolve over time. So the book goes through and it explains some prominent eigenvalues and eigenvectors, right? So our longitudinal modes, we have the short period mode. It's a fast mode seen in the pitch rate and the pitch angle. So it's a very fast modality of our system that's going to affect our pitch rate and pitch angle. Phugoid mode, it's a slower mode, and it's seen in the pitch angle and in our translational velocity u. And these things can be induced by an impulse on the elevator. Then we have our lateral modes. We have our roll mode. So this is a first order fast mode between the aileron and the roll state. We have our spiral divergence mode. And this is a slow mode between the aileron and the yaw and course, as well as the Dutch roll mode. It's a second order mode considers the roll yaw and the side slip. And they describe it as a duck wagging its tail. And we can see these modes really come into play if we have a doublet on the aileron or the rudder. So the key considerations here are that, and in fact, let's go jump into the next slide. So this will help us understand a little bit more of what these modes are. So this is taken directly. I grabbed the section 5.7 description. So we can come in here and we can look at first our longitudinal dynamics, where again we can see that we're talking about the short period mode and the phugoid mode. These eigenvalues, so one of the eigenvalues would be 0. So right there, that tells you that our system is marginally, or is only going to possibly be marginally stable. So small errors are going to cause it to go slightly unstable, or small disturbances. You can't go slightly unstable. You can go unstable. So our disturbances will cause us to deviate. And we saw that when we were looking at our trim, executing our trim trajectories, right? It does it well for a while, and then it gets off. Okay, so then the other four eigenvalues come in two complex conjugate pairs. So eigenvalues always come in complex conjugate pairs. If you have a 0, you're right, unless you're just on the real axis, right? So if you have imaginary components in your eigenvalues, it's going to have a complex conjugate pair. And so the short period mode of our system, if we look at it, we can take our complex conjugate pairs, and for each one of our complex conjugate pairs, we can evaluate its natural frequency and take a look at this natural frequency. So that's going to tell us really how reactive it is. Okay, so the pair with the larger natural frequency corresponds to the short period mode. And so if we come back here, this is the fast mode. So that's where this fastness comes in, as it has the natural frequency that's much larger. Okay, and it has a smaller, the smaller one corresponds to the phugoid mode. So it tells you how to stimulate them. And you can see the response. Okay. Then when you look at the lateral dynamics, there's an eigenvalue at 0 again. There's going to be a real eigenvalue in the right half plane. So this is an unstable eigenvalue. So we know our system's going to diverge eventually. And a real eigenvalue in the left half plane and a complex conjugate pair. So the real eigenvalue in the right half plane is our spiral divergence mode. Okay, so if we come back up here, right, it's a first order really slow mode, meaning that it's actually got a small value in its real component. What this tells us, it's slow, meaning that it is unstable, but it's going to go unstable slowly. So we can execute for a while without deviating too much, right? But that we will deviate eventually. And it's between the aileron and the yaw on the course angle. So once we excite the aileron, then we'll start to see this divergence. Okay, and then so that's the real eigenvalue in the left half plane is the roll mode. So since it's in the left half plane, if we excite it, then it's gonna, since it's in the left half plane, it'll go back to 0. So it's a stable mode. Okay, and the complex eigenvalues. So we have this complex conjugate pair. These are known as the Dutch roll mode. So, and this again tells you how you can excite them. Okay, so we have these various modes, and you can play around with them and really gain more intuition about what these modes do.